Hello, everyone. Good day. My name is Shesha, and it's a great pleasure to be here and to talk about my work on connectivity properties of random reaction networks. This was work I did in the group of Professor Massimiliano Esposito at the University of Luxembourg, along with Noel Freitas. Originally, this was supposed to be presented by Noel, but he is not able to, so I am presenting on his behalf. And I really want to thank the organizers, both for giving me this opportunity to share my work, and also for being very patient. I was supposed to do it in the last cycle, and then I couldn't, and then yeah. So thank you once again to the organizers. So without further ado, let's just begin. The idea of this project, the motivation actually comes from trying to understand the structure of large, complex reaction networks. And again, on your left here, you have a metabolic network. Yeah, I mean, this is a picture that I took from Wikipedia, and and as you can see, it's actually a super complicated network, and it's something that people really want to understand. And if you sort of looked at the number of reactions and the number of species, you have around 1,000 reactions and 1,000 species in this in this network. Whereas a number that comes from cheminformatics and that I highlight here is that if you looked at all possible small carbon molecules, small as in molecular mass within the range of this metabolic network, you would get an astronomically large number. And so, of course, this tells you two things, right? First, that biochemical networks explore or occupy a very, very small fraction of the possible chemical space. And and also they are very understand this structure of these networks. Structurally, is there anything different about a biochemical network compared to a randomly wired network? And this is not a new question. It's a question that people have asked for a very long time. And one way in which they've tried to answer this is by graph approaches. So the typical thing that people do is to start with a reaction, A plus B goes to C plus D, where E is an enzyme, and you project it onto a graph that I show here. So you have 4 species nodes. You have a reaction node, that's the one that I mark in red. And then, the graph sort of connects the species node, the substrates into the reaction and the products out of the reaction. Of course, because the reaction is bidirectional, these edges are also bidirectional. And the enzyme you can choose to keep or leave. For the rest of the talk, I will not for the rest of the talk, the enzyme is immaterial, but you can also connect the enzyme with a different weighted edge if you want to also include the enzyme. Once you do this for every reaction in your reaction network, you then sort of say, I have a graph, in this case, a bipartite graph. How is it different from a randomly wired graph? And if you sort of do this analysis, and people did this in the early 2000s, and if you start focusing on structural properties of this graph, one of the key things you can discuss is the number of connections each node has, the degree. And if you start asking how many nodes have degree k, for the metabolic networks, you'll see that this degree distribution, as it's called, is a power law. And this is, okay, so this paper, this is for different metabolic networks. The same analysis here is repeated for inorganic networks. Whereas the random graph construction that I talked about, that would show an exponential decaying degree distribution. So in principle, this means that you can see that they're completely different objects. Now, this is very interesting, but there are 2 problems with this analysis. The first problem, and again, like I'm not the one highlighting this, this was highlighted much before. The first problem is that paths in graph representations of reaction networks don't really mean much. What I mean by this is that if someone gives you a graph representation, ideally you want it to find connectivity, right? So you want to say, if I give you this input, can your reaction network give you some output? And so let's look at these 2 examples. This is an example that I'll be using throughout my talk. And it just has 3 reactions. So you have A and B, which are like isomers, and you have C and D, which are also isomers. And then you have the second reaction where A and B react to form C and D. And so this is the graph structure. Now you can ask, starting from the molecule A, can I create the molecule D? And the answer for this network is yes, because starting from A, you can make the molecule B, and A and B together can react to form C and D. And so you can also look at the graph structure and say, there is, there's a path going from A to D, and so this is fine. Whereas on the other hand, if you just remove the first reaction, you see that the graph structure still has the path, but you can no longer go from A to D without using the substrate B. In other words, the idea that for a reaction to happen, you need both substrates, that intuition is lost by projecting onto the graph. And this is nothing but the hypergraph structure. So by projecting from the hypergraph to the graph, you're losing this intuition. So either you have to give your graph structure more meaning, which is possible, or you have to start working with some other object. And and what we decided was to see if we could sort of think about these notions from the stoichiometric matrix, which we know is the appropriate description for the reaction network. The second thing is also the null model that you're comparing to in the background. So you create this graph, the bipartite graph, and you compare it to a randomly wired bipartite graph. But I know that chemistry preserves mass and number of atoms. So your random model should also preserve mass and number of atoms. And that is very hard to do at the graph level. And so this sort of brought up two questions for us. The first question was, how do you think about connectivity for reaction networks? And the second question was, can you build a consistent null model of a random reaction network, which also respects mass conservation? And I want to set the notation for the rest of the talk. So this is something that everyone in this talk are very familiar with, but I'll depict a formal reaction like this. Sigma is the vector of species. The nu plus minus rho basically are just vectors that tell you the stoichiometric coefficients of a reaction. Every reaction I consider will be reversible. And by taking the difference between nu minus rho and nu plus rho, you get the number of or the change in the number of counts of each species. And this gives you a column of what is called the stoichiometric matrix. So for the example network that I used before, here is the stoichiometric matrix. In the first reaction, one molecule of A is becoming a molecule of B. In the second reaction, A and B together are becoming C and D. An important constraint that we will always follow is that we will ask that our stoichiometric matrices always have conservation laws. In other words, this is reflected in the left null eigenvector of your stoichiometric matrix. This is because these are conserved quantities under evolution. And in particular, we will ask that a reaction network must have at least one conservation law with all positive entries. And this is the mass conservation. For the example, for this example, in this case, you'd see that the total concentration of A plus B plus C plus D, this vector, is conserved. So when I say that we want to sort of think about connectivity at the hypergraph level, we want to think about connectivity in terms of the stoichiometric matrix. And by connectivity, I just mean how can a given set of inputs be converted by your reaction network into the output. So going back, so the first question that we want to ask is, what is the right way to think about connectivity? And to answer this, I will sort of start at the graph level and then extend the ideas of connectivity in graphs to reaction networks. And so on here, I have a picture of, you can think of it as a graph or a circuit, and I have an input node in red, an output node in green, and in the middle, I have a black box. And this black box is randomly wired. And you don't know how it is wired, basically. And the question is, can you tell me if this red node is connected to this green node? You could do two things conceptually. The first thing you could do is to apply a potential difference. So if you think of this as a circuit, the simplest thing is to put a battery and a bulb in series. And if the bulb lights up, you know that current is flowing through from the red node to the green node. Again, I'm not focusing on kinetics. I'm not focusing on thermodynamics. Maybe the resistances are large. No, we don't care about that. We will assume in an idealized scenario that if you apply the potential difference and and the connectivity is there, the bulb will light up. So this is the first thing you can do. An equivalent thing you can do is to start exploring all paths that go out of this node. So that is like putting a lot of mass on this node and seeing how it diffuses through the network. And what you would see is that you start here. I sort of describe it here. It's like a tree-based exploration. You start here, you go to this node, and then you branch into these two. Eventually, in the limit of very, very, very long time, you should reach the green node if there is a path connecting the two. Now, for a graph, it's very clear that these two ideas are exactly the same. I'm just asking, is there a path that takes you from this node to this node, from the input to the output? I'm just telling you two different ways of finding that. Now, extending that to reaction networks, the first, let's go back to the same example that we had. So you have A goes to B, A and B react to form C and D, and C goes to D. Now, let's assume A is an input and D is an output. So the first method of applying a potential difference, in the context of chemical reaction networks, it becomes applying a chemical potential difference. So in other words, now imagine that you sort of connected your reaction network to a reservoir of A molecules and a reservoir of D molecules. The analog of the current now is that a molecule of A comes from the reservoir into the mixture, reacts, goes through this entire cycle, and then a molecule of D leaves the reservoir, leaving the internal reaction network at a steady state. If this current flow can happen between the reservoirs, that is the analog of connectivity. And this notion, topologically, is what we call emergent cycles. So the idea is that suppose you had a series of inputs and a series of outputs, I will talk about the way you do it actually, but you virtually chemostat them, or you connect them to reservoirs, and then you ask, will this configuration create a non-equilibrium current between the reservoirs? The second idea of just exploring the network, that we call forward reachability. And the idea is that you start with a large amount of the single species A, and you see what products are produced in the limit of very large time. So you start with A. Initially, the first reaction will produce B. A and B then will create C and D. And so this notion is what we call forward reachability. Now, the interesting idea is that the equivalence for graphs is completely destroyed for reaction networks. So in other words, extending equivalent notions of connectivity from graphs gave us two very different ideas of connectivity for reaction networks. And that sort of also tells you why graph-based approaches are not exactly the best things to do while studying reaction networks. And the second thing this tells you is that you need to understand the physical scenario in which you're thinking about, right? If you have an open reaction network, by that I mean a reaction network which can exchange material from the outside, probably you want to think about emergent cycles if you want to think whether some inputs can be converted into some outputs. On the other hand, if you're in a closed reactor, then probably you want to think about reachability, where you're asking, given this initial condition, can I create this product? To go a bit more detail, emergent cycles, as I said, are effective interconversions between your chemostatic species. So what you do is you take your stoichiometric matrix, you cut it up into two pieces called the X and the Y species. And then basically what you see is whether there is a vector in the right null space of nabla X. Any vector in the null space of nabla is called a cycle. So this is an emergent cycle because it's an effective interconversion only of the species that are not exchanged. In other words, it's an effective interconversion of the species that are exchanged, and it does not change the species that are not exchanged. So in this example, the species B and C are unaffected by the interconversion, whereas a molecule of A is becoming a molecule of, it's in fact two molecules of A are becoming two molecules of D. And the sequence of reactions that does this is you have to do the first reaction once, then the molecule of A that comes in gets converted into B. A and B then will form C and D. And so you've used up the molecule of B. And finally, the molecule of C that you created once again interconverts into D by using the third reaction. And effectively, you've taken two molecules of A and created two molecules of D. Now, to convince you that this is actually a useful notion of connectivity, if we once again repeat this thought experiment of removing the first reaction, you will see that there is no emergence cycle. And this is again because, as I said, you need the molecule B to convert A into D. And this sort of tells you that this is a sensible way to think about connectivity for open reaction networks. The second notion, as I said, is what we call the reachable set. And so here again, I start with the same example. Starting from A, you create B, and then the reaction happens, and in the end, you create D. However, you can also reverse the cycle and say, what if I start with D? And in this example, you indeed, starting from D, you can create C, and then D and C together create A and B, and then A creates B. And you see that what I denote here as F is the forward reachable set. So it's the set of all species I can create starting from that species. And these two sets you see are equivalent. However, this is generically not true. Looking at the second example, you see that starting from A alone, I can do nothing because A alone on its own cannot do anything. Whereas starting from D, I can still create everything because D can convert into C and D and C can interconvert into A and B. So reachability is not even symmetric. And furthermore, the second example shows you the inequivalence between reachability and that, whereas D can still produce A. On the other hand, in the emergence cycle, there is no emergence cycle, which means from the emergence cycle perspective, these species are not connected. Whereas from the reachability perspective, D can still make A. So I hope I convinced you that extending notions of connectivity from graphs to reaction networks gives you multiple interesting notions of connectivity that are appropriate for different physical scenarios. And so now I will just jump into the second question. Can you build a consistent null model for a reaction network that preserves mass? And what we realized when we started thinking about this is that you sort of have to, since you want to conserve mass, the simplest thing you can do is to actually start counting atoms. So in other words, we start thinking of molecules as basically as a lump of atoms. So
now it appears.
Every molecule sigma. Now I represent 6, telling you there are 6 carbon, 12 hydrogen, 6 oxygen.
Sorry, Shesha. Sorry to interrupt.
Yeah. Yeah.
So
no worries.
so your voice is cutting out. Maybe do you want to try like turning off your video? Maybe that helps.
Okay. Sorry.
Yeah,
Yeah.
it seems,
I don't know. Did I start too much? I don't know. Did you lose a lot? Is there a
no,
problem?
no. Just
No, not yet.
I think it's
We
fine. Yeah.
Okay.
lost time, maybe 5 seconds or something, but
Yeah.
Okay. So was it just the last slide or?
No,
now
just now it's
the last
fine. Yeah.
sentence for 2-3
Okay.
seconds.
Perfect. Also, I realized that I started talking before you introduced me, so sorry about that.
No
But
worries.
yeah, I know I didn't. Yeah, I just started talking. I didn't realize that I had to. Yeah. Is it okay now? Better?
Yeah.
Oh, okay. Yeah, and questions are welcome all the time. So yeah, please feel free to stop me anytime you have a question, or if something's not working, of course. Okay. So as I said, now we want to go back to the second question. How do you build a consistent null model? And what we realized is that you have to sort of start thinking about atoms. You can no longer think in abstract labels anymore. You have to start thinking about atoms. I mean, again, this is not a big conceptual leap. It's a kind of thing that people have been doing a long time, and some people in the seminar have also put papers on. But what was interesting to us is that nobody had looked at nobody had studied the structures of the resulting networks, or at least nobody had used it to define a random reaction network consistently. And so this, I think, is our main contribution. So basically, the molecule now becomes a vector where each element tells you the number of atoms of each type. And once you have this, the first point is that, of course, I'm neglecting structure. It's a huge simplification. And it also means that I cannot distinguish between isomers, which means I cannot tell you the difference between glucose and any isomer of glucose. So that automatically removes unimolecular reactions from the kind of reactions that I can see, that I can build with this set. But for simplicity, what we decided was that we would only focus on reactions of this kind, where two molecules add to form a third molecule, or a single molecule breaks into two smaller molecules. As you can see, we consistently conserve the number of atoms of each kind. And this means that whatever reaction network you build from this will definitely conserve both mass and atoms. For simplicity, we did not include fully bimolecular networks. You can reactions. You can also include those, and I don't think the results will be significantly affected. Once you've built the full set of reactions, of course, you also have to set a limit. So we also set a limit of the maximum number of atoms of each kind a molecule can have. With this restriction, you can enumerate all possible reactions. With this enumeration, you can now decide to pick reactions with a probability P. This construction is similar to what is called the Erdos-Renyi random graph. I'll briefly introduce that later. But as I said before, this is again an idea that appears on and off in the chemical literature. For example, if you look at polymerization models, if I focus on one atom, that's like having a single monomer, the model that we get is exactly polymerization. So you have two polymers of I and J reacting to form a larger polymer of I plus J. And we say Q is the largest polymer that we allow in our system. And in fact, this model goes back all the way to Smoluchowski, who first studied it for his to study coagulation. And this is a picture that I got from Wikipedia. If you allow for two atoms, the picture is you see that I1, I2, and J1, J2 react to form I1 plus J1, I2 plus J2. And again, you have now Q1 and Q2 as the largest number of atoms of each type that you allow. So what we decided to do with this approach was to say, okay, now that we have this ensemble and we know the two types of connectivity, how do the two types of connectivity look in this random ensemble? And that is what I'll talk about in the last few minutes of my talk. Before I do that, it's nice to sort of establish a baseline. And for that, like I talk about the Erdos-Renyi random graph. So you have n nodes, capital N, and you can pick any nodes between any, you can pick an edge between any two nodes with the probability P. Now, typically the interesting region from a physics-based perspective is you write your probability as some gamma by n, and then you vary this gamma. If you do that, what you'll see is that when gamma is smaller than 1, there are multiple small disconnected components. And when gamma crosses 1, there is one giant component. And this is a percolation transition because you're going from like disconnected graph to a fully connected graph. To a single giant component. And if you're interested, the order parameter is the number of nodes in the largest component scaled by the total number of nodes. So it's the fraction of nodes in the largest component. And this fraction is 0 when gamma is smaller than 1 in the limit of n going to infinity. And it's proportional to gamma when gamma is slightly bigger than 1. And you can see here that it's a simple simulation sort of showing this. The black line is the theory. And the dots, these dotted lines are basically simulations. And you can see that as I increase n, you're approaching the theoretical curve. So what we did was basically try to do a similar idea. So if you now want to think about emergent cycles, what we did was to sort of say that, okay, let's generate multiple random reaction networks. For each network, choose an input and an output. Well, you can actually choose multiple inputs and multiple outputs, but for the simplest case of one atom, you choose one input and one output. And then you ask, is there an emergent cycle between these two? And you average this out multiple times, and what you get is a probability that at a given gamma, you have an emergent cycle between two randomly chosen species. And this is the quantity that I plot here. And as you can see, first of all, that unlike the Erdos-Renyi case where the transition was continuous, in this case, as I increase Q here is just like N, it's the largest species I allow in my this thing. As I increase Q, P is 0 before some gamma star, and then it sort of abruptly jumps. And so instead of a continuous transition, you have a first order jump at this gamma critical. And we sort of estimated this by looking at the crossing points. That's a detail that's not really important. And this gamma star that we have here is a theory calculation that we did. As you can see, like our calculation is not exact, but it gives a very good estimate. And we also repeated this for higher number of atoms. I will not go into that because of lack of time, but if you're interested, please ask me more. We also did the same for the reachability. And here the order parameter is similar to what was in the graph picture. Basically, you say that for every species, you compute its reachable set. And then you choose the largest reachable set. This is just the cardinality of the set. And then you divide by Q. And this quantity, you can see, also has a transition at gamma C is 2.92. It's not clearly visible here, but
Oh.
Yeah, now we've completely lost them.
Maybe even still inside.
yeah.
Yes. Yeah, now we lost you for a while, but
Yeah, so if you go
sorry,
back on
sorry.
the previous slide,
you're
and
almost
explaining the graph in the bottom right. Yeah.
I was explaining the graph. Oh, I'm really sorry for this. I don't know why my connection is so bad. But yeah. Well, okay, I didn't have much to say. It's just that, so here I'm plotting the average of, so for every species, you compute this thing called the reachable set. And the order parameter is basically the largest reachable set, and you scale it out by the total number of species that you've allowed. And I'm plotting the average of this versus gamma. And it's not immediately obvious from this plot, but we could show that there is a critical gamma, which is 2.92. The key difference that I wanted to highlight is that 2.92 is very different from 3.62, which was the critical probability for the emergent cycles, also showing you the difference between these two quantities. So in summary, what we did was to extend two notions of connectivity from graphs, and I showed you that they're completely different in reaction networks, even though they were equivalent notions in graphs. We then formulated a consistent extension of a random graph model, and we studied the statistics of this new measures of connectivity. And both measures of connectivity sort of showed percolation-like transitions. What I mean is that, let me just, I don't know why I can't go back. Sorry. What I mean is that, once again, you see here in this regime, the low gamma regime, the probability of an emergent cycle is 0, which means technically you cannot create one species from another. You cannot create your output from your input with high probability. Whereas here in the high gamma regime, you definitely can. And the same thing for the reachability. You see that the average reachability is very low at low gamma before it starts increasing. So in other words, in both cases, you're going from a disconnected regime to a highly connected regime. And this is, again, a percolation-like transition. Yeah, so if you're interested, please find the preprint and the abstract, the link here. I also have a QR code later. What do we want to do more? Well, one thing we want to do is we want to add unimolecular reactions. And more broadly, we want to start thinking about adding structure into our model. The simple method of doing that is to say for every monomer, you create an excited state. This, I think, is also something that has come up in work of Praful, for example. He has studied similar models, but with respect to autocatalytic reaction networks. And the second thing, I would say another way of thinking about structure is really to think of chemical graphs. So where you start thinking about molecules as graphs and then reactions as things that change or manipulate the graph. And this is a perspective that has come up in the works of Anderson, Flam, and Stadler. And yeah, it would be very interesting to see how to increase, basically how to make our null model more and more realistic by sort of thinking about adding structure. But again, I mean, analytical progress I don't expect there, but yeah. Finally, of course, we are interested in comparing with real world networks and to see, to redo the kind of graph theoretic analysis and to see if really there's something interesting we can say when comparing with real world networks. So with this, I thank you. Here's a QR code again of the draft if you're interested. And yeah, questions, please. Yeah.
Yeah, I can ask already a question to say connected